All right, let's dive into something that's all around us, literally. We're talking about the fundamental states of matter. You know, the solid ground, the water in your glass, the air you're breathing right now. What if I told you they're all basically the same thing deep down? Let's find out how that's even possible.
So, let's kick things off with a little thought experiment. Picture this, a huge, solid mountain, a winding, flowing river, and the wind, which you can't even see. I mean, they seem about as different as you can get, don't they? But they actually share a pretty incredible secret.
And here it is. They're all made of the exact same stuff. The only difference is how that stuff is behaving. And to really understand that, we need to zoom in, like way, way in.
So, what are these universal building blocks we're talking about? Well, before we can get there, we gotta cover a basic concept first. What even is matter?
It's actually a really simple but powerful idea. If something has mass, if it has some weight to it, and it takes up space, then congrats, it's matter. The phone in your hand, the coffee on your desk, even the air filling your lungs, it's all matter.
Okay, so we've got a handle on what matter is, but what's it made of on a microscopic level? This is where things start to get really interesting.
Okay, this is the key that unlocks everything. It's called the kinetic particle theory, and what it says is pretty mind-blowing. Everything, every solid, every liquid, every gas, is just made up of these tiny, tiny particles. And here's the wild part, they are always moving, constantly, randomly. The only thing that makes a solid and a gas is just how those little particles are moving.
So let's really break that down. In a solid, the particles are jammed in there, super tight. They're just kind of vibrating on the spot. Imagine a perfectly ordered crowd at a stadium, everyone in their assigned seat. Now for liquids, things loosen up a bit. The particles can slide past each other. It's more like a party, people mingling and moving around. And then you get to gases. Oh man, it's total chaos. The particles are super far apart, zipping around like crazy. It's basically a massive, never-ending game of dodgeball.
All right, so if everything is just particles moving around, it makes sense that we can get them to move differently, right? And when we do that, that's when matter actually changes its state.
Let's talk about melting. When you add heat to something solid, like an ice cube, you're really just giving its particles a shot of energy. They start vibrating faster and faster and more violently until, bam, they break free from that rigid structure. At one specific temperature, the melting point, the whole thing just gives way and turns into a liquid.
Now what if you keep adding heat? Well, the same thing happens, just turned up to 11. Those liquid particles get even more energy. They start moving so fast that they can completely break away from each other and just fly off as a gas. We call that boiling, and for water, it happens right at 100 degrees Celsius.
But hold on, what about evaporation? Like when a puddle dries up even on a cool day. That's different. Boiling is a frantic, all-at-once event that happens at a very specific temperature. Evaporation is way more chill. It can happen at any temperature, as individual particles right at the surface happen to gain enough energy to escape. It's a much slower and quieter getaway.
And, of course, this whole process works in reverse. If you cool a gas down, the particles lose energy, slow down, and start clumping together. That's condensation. Cool a liquid down enough, and the particles will slow down so much they lock into a rigid structure. And that, my friends, is freezing. It's all just about giving or taking away energy.
We can actually watch this whole journey from solid to liquid to gas. There's a cool tool for it called a heating curve. It's like a roadmap for matter as it changes states.
So, what is a heating curve? It's basically a graph. On one axis, you have temperature, and on the other, you have the heat being added. It lets us track exactly what happens to the temperature of a substance as we heat it up and watch it go from a solid to a liquid and all the way to a gas. But there's a really weird part of this journey.
This is where things get a little strange. When a substance is actually changing its state, its temperature stops rising. It just flatlines. I mean, think about that. You're pumping heat into a pot of boiling water, but the thermometer stays locked at 100 degrees until all the water is gone. Why? Because all that extra energy isn't making the particles hotter. It's being used for a very specific job, breaking the bonds that hold them together. Only after the mission is complete and the state is fully changed can the temperature start climbing again.
Okay, for this last bit, let's zoom in on gases. This is where the particles are at their most free, and the way they behave is just, well, it follows some really neat rules.
The rules for gases are actually pretty intuitive. If you heat a gas up, its particles get a huge energy boost and start moving way faster. They smash into the walls of whatever container they're in with more force, pushing those walls outward. So more heat means the gas takes up more space. Higher temp, higher volume.
And what about squeezing a gas? Well, if you increase the pressure, you're literally forcing those fast-moving particles into a smaller space. There's nowhere else for them to go. So you crank up the pressure, the volume goes down. Simple as that.
All of this constant random zipping around leads to another really cool effect called diffusion. You've experienced this. When someone sprays air freshener on one side of a room, you eventually smell it on the other side, right? That's because those particles naturally spread out, moving from where they're crowded to where there's more space, until they're evenly mixed.
And here's a fun fact. Not all gases diffuse at the same speed. It turns out lighter particles can move a lot faster than heavier ones. Think about helium versus oxygen. The tiny, lightweight helium particles can zip around much quicker than the heavier oxygen particles. It's actually why a helium balloon deflates so fast. Those tiny helium particles are literally sneaking out right through the material of the balloon.
So, we've seen that the world around us is really just a dance of countless tiny particles, jiggling, sliding, and flying around. But that leaves us with one last big question. If that's all it is, what are the powerful, invisible forces that hold those particles together so tightly that they create something you can actually touch, something that feels solid? Well, that's a story for another day.